Um, so it might be as long as War and Peace. And it's nice to know about the Nobel Prize prospects, because you can always win too. Okay, it's really a pleasure to be back here at NYU, where I have not been for many years, and to see a physics department that is truly flourishing, and to give a colloquium in this extremely small kind of cavern. So, I will indeed talk about quantum field theory, past, present, and future. And, you know, quantum field theory, which to some sense, if you ask what is the world made out of as we understand it today, probably quantum field theory is the framework that underlies everything we know for sure, is solidly based in experiment and in theoretical understanding. And so I'm first going to discuss a bit of the history, take us up to the present, and then speculate a bit about the future. Stages of development of quantum field theory, as many areas of fundamental science. Are we under the subway? Is a story of confusion and then triumph, and then confusion again, and so on and so on. And quantum field theory is no exception. Begins with the notion of the field, which in my view was the great achievement of the 19th century and the beginning of the 20th century. Classical field theory, the concept of a field intuited by Faraday and put into mathematical form for electromagnetism by Maxwell, and then extended by Einstein to the metric of space-time itself. That was a period of great triumph of classical field theory, followed by much confusion when quantum mechanics came along, and Dirac showed you invariably had antimatter present in any quantum version of quantum field theory, and there was a theory, Maxwell's theory, as well as Einstein's theory, ready to quantize, but much confusion, which ended with, in the late 50s, with the development of what we might call quantum electrodynamics, perturbatively constructed, renormalization theory, and an incredible triumph of these ideas in agreement with experiment. But following on that triumph of quantum field theory, the first triumph of the quantum version of field theory, there was the attempt to apply those ideas to the other forces of nature, in particular strong and weak nuclear forces that were then being explored experimentally, and an incredibly confusing period followed, which led into the 1970s, where all sorts of new techniques and understanding and concepts were developed, culminating in the formulation and, over the last decades, verification and further understanding of the Standard Model, an even greater triumph of quantum field theory. But then, towards the end of the last century, we turned our attention to Einstein's field theory, that of gravity, and to the unification of the forces, and were led off into strange directions, string theory, quantum gravity, and I would say that now we are in a period, once again, of great confusion. For those of you who are just beginning your research work in fundamental physics, it's, in a sense, much better to be in a period of great confusion. The interesting questions lie before you to be answered. So the notion of a field is quite amazing for us to look. If you look back and read textbooks on the beginnings of 19th century textbooks on electromagnetism, you'll realize how confused people were about the notion of a local variable, a field that had an independent dynamical existence labeled by points in space and time and obeyed partial differential equations. Classical physicists originally could not conceive of a dynamical entity that had an existence of its own, independent of describing the coarse-grained macroscopic properties of some medium, and were totally confused by, well into the beginning of the 20th century, into what fields really were and what Maxwell's equations really taught us. And it's a wonderful history. Starting with Faraday's lines of force and his totally intuitive, non-mathematical intuition as to the physical existence of a field that pervades space. Einstein explained much of that and dismissed the ether forever, and the fields acquired their own independent dynamical existence, but even more extended this notion to fields that govern the metrical structure of space-time. And both of these, electromagnetism and general relativity, are magnificent achievement of the classical, that is the ultimate triumph of classical physics. Together with the other great achievement, by the way, of the 19th century, which I think is thermodynamics and system mechanics, which transcends all theories in a way. But with the advent of quantum mechanics, it was clear that one had to describe these fields quantum mechanically. And here, in a sense, the big breakthrough, I think, happened with Dirac's attempt to describe a single electron. Not a field, but an electron. But Dirac's equation, so successful in describing, explaining the hydrogen atom in a relativistically invariant way, and so on, predicted antimatter. One of the greatest, in my opinion, theoretical predictions ever. It's sort of like supersymmetry. For every particle, there is an antiparticle, most of which at the time had not been discovered, except for the photon, which is its own antiparticle. Dirac's equation led to the realization very early that for every particle in nature, given the within the framework of relativistic quantum mechanics, there must exist antiparticles, particles of the same mass and opposite conserved quantum numbers, antimatter, and anti-electron, the positron, whose discovery confirmed this picture. But it meant that you could no longer envisage particle theories, but rather you had to deal with many-body theories or quantum field theories. And there was one around, ready to be quantized and already present, and quantum aspects were discussed in the beginning of quantum mechanics, namely the electromagnetic field. So from the early 30s, the task was obvious. Should quantize the electrodynamic Maxwellian field theory, and couple it to the electron field that described whose quanta were fermionic electrons. Now, this was in a sense straightforward. The principles were all there, and the formulation of quantum field theory applied to electrodynamics was written down shortly after the Dirac equation by Dirac and Heisenberg and Jordan and Wigner and so on. But it still took over 25, almost 30 years to develop this theory. And partly, it was because there were a lot of problems. But they were all, in a sense, technical. Looking back, when people started, they thought these were deep conceptual problems. Another revolution was around the corner. Totally wrong. The problems were gauge invariance, UV infinities. There were no calculational tools to speak of. They're all technical issues. historically, the real problem I think it took so long was that the Dirac equation worked too well, you know. There wasn't that much motivation to improve on the single particle treatment because the corrections were so small and took a long time to be able to see the quantum effects of quantum field theory till radar and other modern experimental techniques were developed after the war. But once that happened, solving these technical problems and tackling the obvious task of quantizing the electromagnetic field that was achieved by Feynman, Schwinger, Tomonaga, and explained by Dyson, we sort of knew what quantum field theory was. And I'm now going to give you not a description of what quantum field theory was by the 1960s, the way I was taught quantum field theory, and not for electrodynamics because there are too many indices, but for a theory which there's only one quantum field, phi, which describes a scalar quantum field with no other quantum numbers. So the approach then was that one had a Lagrangian whose integral gave an action, whose stationary points gave the classical equations of motion of the quantum field theory, and one had to quantize that system, write down a Hamiltonian, canonical coordinates, impose commutation relations, set of Poisson brackets. In principle, they were following the path laid down by the founders of quantum mechanics. This is an example of a Lagrangian, a local functional of quantum fields. Locality was recognized as an essential component to achieve relativistic invariance. Second order partial differential equations, that was ensured by only having second derivative, quadratic derivatives here. The potential or the interaction terms were arbitrary polynomials in the field. Why not? This is a Lagrangian one can write down classically. It gives second order differential equations for the fields, and you can quantize it. But there was something special about these terms and not these higher order polynomials. In my day, one said that these terms define a renormalizable theory to which you could apply renormalization theory, which was the big achievement of this group who learned how to deal with the infinities that occur in calculations, perturbative calculations. And the essence of that approach at the time was one can choose these parameters, which have kind of a physical definition, m being the mass of the scalar particle whose the quanta of this scalar field, g being a quartic coupling that describes interactions of these scalar fields, the coefficient of the kinetic term defining sort of the arbitrary normalization of the field. When one has to choose the parameters that appear in the Lagrangian to depend on an ultraviolet cutoff that must be introduced to define the theory, otherwise you would encounter infinities. And you can choose these parameters order by order in perturbation theory in the small coupling. Here G, but in QED, the fine structure constant, so that the physical observables that you could actually measure, the mass of a scalar particle or the coupling of the particles, be finite functions, and any other physical observables like S-matrix amplitudes, be finite functions of the finite parameters that you can measure, the mass, G, as you remove the ultraviolet cutoff. The ability to do this was restricted to theories which did not contain these higher order terms. Phi 6, phi 7, phi 8, phi 9, an infinite number of polynomial terms could be introduced which were local, relativistically invariant. These were renormalizable interactions according to the prescription of renormalization theory. These were non-renormalizable, and the philosophy was, an infinite number of such terms, you put them in. You can't really achieve this anymore without an infinite number of terms, which means your theory would depend on an infinite number of parameters. That's bad, because you can't calculate anything, therefore they're not allowed. Interesting idea, right? Not surprisingly, people felt that this was a bit of a trick. You were sweeping infinities under the rug. You weren't really explaining why these terms didn't exist, except the fact that you couldn't calculate anything if they did. So it's very interesting that Feynman, one of the famous developers of this approach, said in the Solvay meeting in 1961, not sure whether this was after he got his Nobel Prize for, no, before. But still, QED had been established. I still hold to this belief and do not subscribe to the philosophy of renormalization.
Can you say what this belief is?
This belief of the validity of this trick, renormalization theory, of this way of defining quantum field theory. The philosophy of renormalization. So the trick, order by order, you adjust these bare parameters, the parameters that appear in the Lagrangian, as functions of the cutoff. Take the cutoff to infinity, make sure that the physical, fixing these few parameters, you can fix these few parameters, choose these as functions of the ultraviolet cutoff and the physical parameters, and then all physical observables are then finite. Most of the founders of quantum field theory believed this was, although it worked, was a trick. Something was not kosher about it.
What's the difference?
And what they really believed in that there...
the philosophy of renormalization.
Yeah. That's what he developed. He was, yes, right. He didn't subscribe to the philosophy. I think his belief was that there would be something better. I forget exactly. I should have had the full quote. Look it up. But mostly, this is what he meant. Dirac gave up on quantum field theory, tried many ways of modifying classical field theory so as its quantization would be okay. I had long arguments with Wigner in Princeton about none of the founders really took this seriously. But it worked. And I enjoy always giving these precise examples of the unbelievable success of quantum field theory. This is the calculated G minus 2 the electron to, this is the measured value to 5 parts per trillion. And I'm sorry, that's the theory, and the experiment's a little better. 5.3 parts per trillion now. And this, every physicist should just look at this and feel pride as a community. It's, after 400 years, can achieve a precision of 1 part per trillion and agree. Both calculation and experiment are unbelievable towards the forces. I mean, they're heroic efforts.
G minus 2 is 1,000th the precision.
Of what? Sorry? Say it again?
G minus 2 because you have, well...
You're arguing about the 2. I'm presenting this in the way that looks the best. G minus 2. But it's true. I mean, all these digits have to agree, right? It's just truly unbelievable. And, should be really give us, and it does give us, both pride and the necessary arrogance to go on. It's quite amazing. But this worked so well that people stopped trying to really understand why it worked so well, because then they would start getting confused, as Feynman did as he spoke. And this was even though the series that one is summing, these expansion terms, you go out far enough, it's going to begin to deviate from the true measurable answer. This series diverges, has 0 radius of convergence. It wouldn't even help you if alpha was even smaller. then 1 over 137. This this series has 0 radius of convergence, we believe. So what are we doing? We believe we know the answer to this, and the nature of the divergences is fascinating and important, and is such asymptotic series until you get to the 137th term are still very useful. Even though, even more, we believe that this theory as such, QED all by itself, probably doesn't exist, is a sick theory. Nonetheless, so the real source of confusion, however, for the strong and weak nuclear forces was not so much in these foundational issues of quantum electrodynamics, but rather in the fact that our understanding of quantum field theory at the beginning was totally based on perturbative techniques, Feynman diagrams. So I took 2 courses in quantum field theory at Berkeley when I was a student, one from Stanley Mandelstam, who gave a rather traditional course, and one from Steve Weinberg, who gave an untraditional course, in which he, first lecture started out saying, field theory equals Feynman diagrams. That today would be regarded as a very naive and incorrect point of view. But that's all we had, and that's all they had. And the Fermi theory of the weak interaction was even worse. So Fermi had a Hamiltonian theory model of the weak force, the weak interaction, which was quite successful because at that time, in the experimental range that was being measured, the effective coupling was very small. So one could just do Born approximation, get good results. But if you tried to include quantum corrections, this fell into the non-renormalizable, forbidden category of theories. So one didn't know what to do. Now, remarkably, the theories that provided the answer, the generalizations of electromagnetism, of Maxwell's theory, the non-abelian gauge theories, were invented way back, 1954, which is 60 years ago. But they had all sorts of problems, so people were confused. They had massless bosons, which were not observed. They tried to couple them to non-conserved currents, like flavor, not an exact symmetry, which made no sense. And when I was a student, the reigning philosophy, certainly on the West Coast and certainly of my thesis advisor, was a very totally different approach to fundamental physics based on concepts of nuclear democracy and the bootstrap, which was essentially a desperate attempt to deal with the strong forces where one couldn't find the elementary constituents that made them up, so the many, many resonances that were being discovered every month, all these hundreds, dozens of nuclear particles, equally fundamental, it seemed, as the proton and neutron, were all equally fundamental. That's nuclear democracy. And there were no equations. There was no Lagrangian. There were just furthermore, fields. Who's ever measured a quantum field? Especially in the case of the strong interaction. So you shouldn't formulate the theory in terms of unobservable quantities. This is a feeling, by the way, that continues to pervade physics. Comes back in different forms today. One should always stay with things that are observable. It started with Einstein, Heisenberg, and so this idea was general principles determine a unique S matrix. And you don't need equations, and you don't need Lagrangian or Hamiltonian, just general principles. That's the bootstrap. Yeah. Didn't work very well. Now, there was a similar reaction against quantum field theory in the Soviet Union, led by Landau, and in the late 50s got interested in the problem of quantum field theory, describing mesons and strongly interacting particles. And he and his group discovered what's called the Landau pole, or the zero charge. And that was the observation in all theories that were studied, and there weren't many that they studied, QED, for example. The physical coupling, the one you actually measure, vanishes no matter how you adjust the bare coupling. So if you go beyond perturbation theory, which they did by rather crude techniques, but ultimately they got what we think is the right answer, and you try to adjust the bare coupling, the one you put in the Lagrangian, or in effect the one you measure at arbitrarily short distances locally, and you want to get a finite measurable 1 over 137, for E squared charge of the electron, you find you can't. As you take the ultraviolet cutoff to infinity, they saw in some illegitimate but correct approximation that the physical charge depended on the bare charge in this way. So as you take the cutoff to infinity, no matter what value you choose for the bare charge, once you've summed all the perturbative terms to get this non-perturbative solution, you find the physical charge vanishes. So this was the problem of zero charge. There are other ways of looking at it, which gives rise to the name the Landau pole. What it really is the phenomena, this kind of charge renormalization should be understood physically as simply dielectric screening. The vacuum in quantum field theory in a quantum mechanical many-body system is a medium full of virtual particles, antiparticles. It affects the charges much as a dielectric medium affects the electric charge by screening. So the virtual positrons and electrons in quantum electrodynamic vacuum screen any charge you put into the medium. And since in a local theory you're interested in putting the charge in at an infinitesimally small point, logarithmically, if you think by scales, that's infinitely removed from the scale at which you measure the charge. And there's so much screening that no matter what charge you put in, it's screened to zero, and there is no physical charge. That's the physics of it. Natural. And they believe, Landau, being a bold man, and therefore only sometimes correct, leaped to the conclusion that this was true of every theory, every quantum field theory. And it is for all non-asymptotically free theories. Well, the phenomena is, well, the screening is true for sure. He came to a very dramatic conclusion that within the limits of formal electrodynamics, a point interaction is equivalent for any intensity whatever to no interaction at all. And therefore, we want to apply this not to QED, where, this is a problem for the ages. You could cut off the theory and not worry until you get to extraordinarily high energies. But for the strong interactions, you already started with strong coupling, and you couldn't do perturbation theory, so you had to confront this problem immediately. And he was driven to the conclusion that the Hamiltonian method, by which he meant quantum field theory in effect, method for strong interaction is dead and must be buried, although of course with deserved honor. And he said, it is well known that theoretical physics is almost helpless in dealing with the problem of the strong interactions. By now, the nullification of the theory, quantum field theory, is tacitly accepted even by theoretical physicists who profess to dispute it. And this is evident from the complete disappearance of papers on meson theory, the idea of trying to take mesons and nucleons and construct a field theory with mesons, or heavy mesons replacing massless photons as the mediator of the forces. And particularly from Dyson's assertion that the correct theory will not be found in the next 100 years. Dyson, too, likes to make dramatic predictions, which are invariably wrong. Landau said this in 1960, just before his tragic accident. And it only took 13 years to get the theory. So he was quite off. And, you know, the big conceptual revolution, in my opinion, in this game of quantum field theory and critical phenomena is due to Ken Wilson's understanding of the renormalization group, which I'll say a word about, and its application initially to critical phenomena. So, Wilson, in trying to understand the renormalization theory much more deeply, and in particular the renormalization group, which I'll explain in a moment, finally realized that at a second order phase transition in many body systems, where the correlation length becomes infinity, a discrete many-body system, solid, can be equivalent for large, measurements at finite distances to a continuum field theory. And so he, who was mostly interested in particle physics, could test out his ideas in critical phenomena, which are, in some sense, simpler than figuring out the standard model. And aside from everything else, and this led to this wonderful reconciliation of particle physics, quantum field theory with condensed matter physics, fields which had gone their own way for many decades, but were now came back together again. And it led to a totally radical re-understanding of what quantum field theory is and the notion of effective field theory. So let me just say, well, the general notion, of course, is of the different ways we describe physics at different scales. And we all know this is part of the deep structure of nature, the separation of scales. It's hard to imagine physics without that separation. And so it's always built in some sense the way we think about nature. For example, if we want to understand nuclear physics, we might start in a reductionist sense with string theory, or as an example of a theory that might be applicable down to very short distances, the Planck scale, which quarks, for example, are pictured in such theories, such descriptions as vibrating strings. The quark has the structure, and there it is. But if we're interested in describing quantum chromodynamics at distances of 10 to the minus 16 centimeters, where we probe the structure of the proton, we use QCD. Now, if we could, in effect, derive QCD from string theory if we knew where we're starting from. But there's a perfectly effective description of whatever the microscopic theory at the Planck length is in terms of QCD, which is a quantum field theory, where basic fields describe quarks and gluons. And we describe, in some region at least, the scattering of hadrons, of nucleons by quarks exchanging gluons. A description that works for certain high energy events very well. But if we wanted to go to larger scale measurements and describe nuclear physics, properties of protons and neutrons within collective bound states nuclei at low energies, at larger distances, size of the nucleus, then we construct an effective description in terms of protons and neutrons and pions, which are bound states of quarks, but we can ignore that, describe nuclear physics. And of course, if we want to do atomic physics and chemistry and biology, it's quite enough to take the nucleus and replace it by a point-like particle. We only care about its charge and its mass and its spin. At nanometers. And so on. We can keep going till we get to fluid dynamics, the Navier-Stokes equations. And now, this is actually a rather deep element of nature, which we all take for granted. And at each stage, there's an effective description, which is quite complete, uses input that could be derived from the more microscopic description. And it's absolutely clear that we never would have made any progress in science if there hadn't been this separation of scales. What that last statement implies, actually, I don't know yet, but but it's a very important statement. You can imagine having to understand string theory in order to figure out the Bohr model or the structure of atoms. But there is a very precise way, at least in the framework of quantum field theory, that this effective dynamics is realized, and this was Wilson's great contribution. So the decoupling of physical phenomena at different scales is clearly an essential feature of nature. Nature of our description changes as we consider different energy scales. We use different variables, different force laws, different everything. And in a very general sense, what we mean now by the renormalization group, which has more technical descriptions, is how to systematically describe the change in our description of nature as we integrate, as we go from short distances to large distances, as we say, I don't care about what happens at short distances or fast time scales. We will integrate out those degrees of freedom and just try to construct an effective theory of the larger distance, slower degrees of freedom. And what Wilson really discovered was that as you do this and go to larger and larger distances, ignore more and more things if you want, that this can be regarded as a flow in the space of theories, and that can be made very well defined within the framework of quantum field theory, and that the flow, the solutions of this group of scale transformations to larger scales approaches a finite dimensional submanifold in this bigger space, which defines then these effective low energy theories. Now, one of the nicest ways of visualizing this is based on the idea of block spins that was Katanov's intuitive picture of how this works, where you imagine a system defined, say, on a lattice. This could be a many-body condensed matter, bunch of spins on some lattice with spacing L. So at each point of the lattice, there's some dynamical variable. And you need all, there's some Hamiltonian, I'm not going to write down, some theory defined at this scale with some force law, Hamiltonian, with local interactions. And you need all that apparatus if you're doing measurements at the scale of the ultraviolet cutoff, which here is the lattice spacing. And it's described by some Hamiltonian. Now, Katanov said, well, I'm interested in very large scales at very large measurements because I'm going to a critical point where the correlation lengths become infinite. So I'll just look at very large scale correlations. So I might as well ignore what goes on at length L and construct a Hamiltonian that would describe correctly, or even exactly in principle, the physics at length 2L. So that means I'll get rid of the first Hamiltonian, replace it by a second Hamiltonian, which I can do by various techniques, some exact, some approximate, given the microscopic Hamiltonian. And I can repeat this over and over again until, in a sense, I go to infinite size. And in that process, I will arrive at a Hamiltonian which will be adequate for describing the large-scale behavior. And in such a flow, conceivably, there could be a universal behavior. No matter where you start, you approach the same submanifold, sub-Hamiltonian, and do what those guys wanted to do, which is calculate certain observables which are universal features, don't depend on what you started with here, but only will end up at the same point. So, what is quantum field theory? Let me give you the modern version, which is based on this whole idea. So now we generalize a bit, write our Lagrangian as a sum of local terms. And what's important to know about these local terms, like powers of a scalar field, is their dimension. Their physical dimension in units of mass or inverse length. And since the Lagrangian density has dimension d, in d dimensions, 4 in 4 dimensions, mass, energy to the 4th power, and energy density. The dimension of the couplings that appear here, multiplying the various functions of the field, local functions of the fields, have dimension d minus di. And you introduce a cutoff, because you have to always put the theory on a lattice or put some kind of ultraviolet cutoff into the theory. And again, you write down the Lagrangian in this way. But you now look at the various terms. You divide them up into 3 classes. This is now, I'm working now in 4 dimensions. This is so-called irrelevant operator with dimension less than 4. These are marginal operators, which naively have dimension 4. This is inverse length squared, derivative is inverse length, field is inverse length, and so on. So all these are irrelevant operators, where the coupling here is not dimensionless, but rather has dimensions of length squared, and so on. These are so-called irrelevant operators. Now, one says that this is a theory defined at a length scale characterized by the ultraviolet cutoff, a very short distance scale, the ultimate lattice of the world, or 0 in the limit, or in terms of energy, very high energy scale. And in order to understand what this theory like this predicts at low energies, one integrates out the high energy degrees of freedom, or reduces the cutoff, if you want, enlarges the lattice spacing. And there is a systematic way, in principle, where you proceed to do that. And just on dimensional grounds, you can see that terms like this, which are, if you go to very large distances, since these couplings have dimensions of length, they must be divided by your length scale, 1 over lambda. And therefore, if you're interested at large length, these become irrelevant. So if you're interested in physics at a large scale compared to the ultraviolet cutoff, these terms, although they're infinite number of irrelevant operators, are indeed irrelevant. They're naturally suppressed, as long as they start out to be, finite in value, suppressed. This, by the way, is exactly what Landau said, but understood in a different fashion. And furthermore, these parameters that characterize the marginal terms that are dimensionless, just numbers, also vary. The effective description requires a change in these marginal terms as you integrate out the momenta, and they flow according to equations. This is the so-called beta function. These parameters are very relevant masses. And so you better ignore them if you want to continue to do this, otherwise they totally dominate and you have nothing interesting. And condensed matter physics, you go to the critical point by adjusting these to vanish. And, but there are only a finite number of them. Because in order to have a local theory, you have to construct polynomials in the field phi, the quantum field. 1 over a quantum field makes no mathematical sense, no matter how you look at it. So in this approach, you're restricted to having a finite number of operators you can construct by multiplying fields of low dimension and an infinite number of high dimension. So in this space of quantum field theories, there's infinite dimensional space, but at low energies, only these and these matter. So now we have an answer to the question of why do we take QED and restrict our attention to the renormalizable terms. It's because there probably are an infinite number of other terms. They're just irrelevant at the energies we're exploring. If the cutoff is at the Planck scale, these are suppressed by, maybe factors of 10 to the minus 20 or 10 to the minus 40, because the Planck scale compared to where we do experiments is a scale factor of 10 to the 20. So turning this around, we've explained why, in attempts to construct theories of particle physics, one restricts oneself to the renormalizable, finite set of renormalizable interactions, simply because the others don't matter.
Is that because we're lucky?
No, we just are big. So we now are trying to go the other way, by the way. We want to actually know what happens at the Planck scale. And if you want to know what happens at lambda, then all of these become important at high energy, and that's our problem now. That requires other techniques. But at low energies, now, it's not just that. It's also, we're also interested in those dimensionless couplings, and that's where, the real differences between the renormalizable terms that survive matters. So in Wilson's breakthrough was really important conceptually and took a long time to sink in, but students nowadays start from there. They don't have to go through the mistakes of the past. We also learned how to quantize these non-abelian gauge theories to break the local symmetry. That's the so-called Higgs, Sprout, or Glare, boom, 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 mechanism, recently receiving so much attention. And we discovered that in some cases, theories behave exactly the opposite to the ones that Landau thought were universal. That instead of screening, you have anti-screening. Instead of the couplings becoming larger as you go to short distances, and then they're screened to their physical values at ordinary distances. They become weaker as you go to short distances, and then are anti-screened as you go to larger distances, and that led to QCD. And we developed a lot of non-perturbative tools. Nobody would argue anymore that quantum field theory equals Feynman diagrams. And in fact, most interesting quantum field theories, we explore the most interesting features thereof using non-perturbative techniques. So in QCD, lattice gauge theory, put the theory on a lattice, do Monte Carlo, solve it numerically. Semi-classical techniques, including instantons, so on, solitons. Actually, methods to make sense out of this divergent perturbative expansion are related to those semi-classical tools, and so on. And then we end up, actually, in the end, with what I regard as the perfect theory. It's not just out of pride, but QCD as a quantum field theory, if it wasn't for all the rest of the stuff in the world, would just be perfect. What do I mean by that? Well, because of this phenomenon of asymptotic freedom, it actually has no infinities at all. The thing that really bugged the founders of quantum field theory were these infinities, and this trick of getting rid of these infinities and renormalization all seemed fishy. But QCD has no infinities, period. I'll say a word about that because some people might be confused in a moment. The other feature it has, which makes it perfect, is that in a real sense, except for those pesky quark masses, it has no adjustable parameters. One of the goals of physics is to calculate everything. Any dimensionless measurable number should be calculable, 1 over 137. So at QCD, without quarks, without massive quarks, which we don't have to put in, so those are adjustable. Without massive quarks, there really are no adjustable parameters. And then, unlike every other theory we've ever had, because of asymptotic freedom, there's no new physics when you go to in the hard direction. The hard direction is going to shorter and shorter distances. And QCD, things get simpler at shorter and shorter distances. The theory becomes trivial. So there's no breakdown within QCD itself, within an asymptotically free theory, no matter how high the energy is, no matter how short distances you probe. So what do I mean by saying there are no infinities? Well, there truly are no ultraviolet divergences. The bare coupling, the one that's defined in the Lagrangian, if you want, at a point, is 0. It's not infinity, it's 0. And then you have anti-screening that builds up a finite charge. And the only time you find infinities, if you calculate in the theory unwisely by expressing observables measured at finite distances in terms of those measured at infinitely small distances. So, coupling at arbitrarily short distances is 0. And of course, if you divide any finite number by 0, you're going to get infinity, but that's not a real infinity. And in fact, the proof of the pudding is that when you try to solve QCD, calculate the mass spectrum, you put the theory on a lattice. Lattice has spacing A, that defines the ultraviolet cutoff. You want to take the spacing to 0. There's a coupling that enters into this partition function, which is a well-defined integral in a finite volume lattice theory. And then you have to choose, in accord with the renormalization group and asymptotic freedom, you have to choose GA to vanish, like 1 over log A, as A goes to 0. But no infinities, ever. And you're guaranteed that the results you get for correlation functions, masses, anything, finite distances, are finite. There are never any infinities. Not only that, there are no adjustable parameters. So you might, I always like to explain in popular textbook where your mass comes from. So imagine you have a theory of QCD with massless quarks. You wouldn't lose weight having massless quarks. The mass of the quarks contributes almost nothing to your weight. It all comes from the kinetic energy of the confined gluon field. And there's no adjustable parameter. What happens is you have these quarks rattling around in a region. They can't get too far apart because of asymptotic, the coupling gets stronger and stronger as you try to pull them apart. So they're confined. They're confined in a ball of some radius. And their energy is just the kinetic energy of these quarks and the gluons rattling around in this ball. And the mass, the value of the coupling that determines the mass, is determined once you know the size of the ball. Now you need some way of measuring lengths in this theory, which has naively no length in it once you turn the quark masses to zero. So take the size of the ball or the mass of the proton. Then everything else is calculable. All mass ratios, dimensionless numbers, are pure numbers. And the task of physics in the next few hundred years is to calculate those numbers, maybe exactly. Who knows? All mass ratios are calculable. Any other physical observable is calculable. Coupling has disappeared to be replaced by a mass or a size of one of the stable particles, if you want. So, this is an approximation to the formula where the mass is related to the bare coupling. And as I said, right, and I remarked on this when I talked to the students today, you also solved Dirac's large number problem. Who wondered why the Planck mass was so much bigger by a factor of 10 to the 19 than the proton mass. Well, in this theory, if you start with any coupling, reasonable value of the coupling, like 1 over 137 or 1 over 50, something like that, at the fundamental scale of physics, the Planck scale, then the size of the proton, which determines the mass of the proton, is defined by how the coupling grows as you go to lower energies. That defines an energy. And since this fall off is logarithmic, it means that this very small number that Dirac was concerned about, 10 to the minus 19, is actually e to the minus some constant over a number of order, 1/20th, 1 over 137. Doesn't really matter too much. Roughly explains. And in real unified theories, this is much more precise. So we could, logarithmically or qualitatively, we understand this large hierarchy of scales. The reason the proton is so much higher than a fundamental scale where we might say the ultraviolet cutoff is this logarithmic running of the coupling. And it works. So this is with the quarks. The agreement now is, as you know, quite spectacular, 1% for the hadronic spectrum. No free parameters, except for those damn quarks. No new physics is required. So that's what I mean by a perfect theory. And it's the first example of a complete theory, no adjustable parameters for getting the mass of the quarks, and no indication where it must break down. And unfortunately, or fortunately, there are questions you might ask even within QCD, like why 3 colors, or why quarks, and why do they have their masses that they do. And then, as you all know, there are other things in nature. But at least this subpart, and this, in a sense, gives enormous confidence in this framework of quantum field theory, at least for this class of theories. But there are all these other parts of nature, and they're not contained in the standard model, which is more than just the strong interactions. The weak interactions are also asymptotically free, so they're nice as well. There's the Higgs mechanism that breaks the symmetry, so it manifests itself very differently. Then, of course, there's electromagnetism, which isn't asymptotically free. So as it stands, the standard model is makes sense to arbitrarily high energies or short distances. But it's certainly the most successful physical theory that physics has ever had. It's quite amazing. It really deserves to be put on a t-shirt. And it deserves to have the model removed, because it's definitely a theory. We've never had a better theory in physics. It works over an incredible range of distances, 60 orders of magnitude, perhaps, and with extraordinary precision of tests.
Those t-shirts on sale in the lobby?
But there is physics beyond the standard model, and here, I should proceed a little faster. You all know that there's physics beyond the standard model, and the thing that I want to spend a bit of time on is string theory, where we've been driven in the search for unification with gravity. And, but string theory, which is this year 46 years old, quite amazing, started as an attempt to explain the strong force. And in a sense, the reason it grew out of phenomenology of strong interactions, nuclear forces, was the fact that if you take a quark and an antiquark and pull them apart, the chromodynamic flux is squeezed by the medium, the vacuum, to a tube. That's why you get this confinement. That's why you get a constant force between, it's just the tension of this fat string. So the reason people were led to string theory by thinking about nucleons and mesons in particular was this physics that's really there. And we believe is probably a very good string theory description of QCD, which we haven't yet perfected. But that's where string theory originally came from, an attempt to describe such flux tubes, in effect. Open strings, we say, with quarks at the end, or just labels, which it was eventually realized could describe gauge mesons in a gauge theory. But it was also realized that you could always close. In fact, you had to. Once you had strings, they could be closed. And those closed strings had gravitons in their spectrum, massless spin 2 particles. And so you automatically got out of string theory gravity. Now, string theory originally appeared to be both a radical change of point of view. Radical in the sense that instead of having point-like objects, local field theory, point-like electrons, quarks, etc., you had extended objects like strings. That seemed quite radical and had radical features. For example, because of the extendedness, because the approach was based on extended objects, you never got ultraviolet divergences at all. There were no such thing. But it also was not that radical in the sense that you could see how quantum field theory emerged as a low energy approximation. So, there are other attempts to modify physics where you go off the left field and you have no connection back to where you where you're on sure ground. That was never the case with string theory. And this early discussion was the first connection, it was the first indication that there's some kind of connection between gravity and these gauge theories. And over the years, we've had one duality after another that has illuminated string theory and illuminated this connection. In the beginning, there was the following duality, which, was sort of, I don't want to go into the history of string theory, but, when you scatter particles, this particle plus this one go to this final state, and describe it by Feynman diagrams, there's two ways that this scattering can happen, right? These two particles can annihilate, and then this particle can decay to others. That's the S channel. Or they can exchange a particle in the P channel. In string theory, this is described by saying that a string, you see, comes in and joins onto this disk and then goes out. This picture describes at the same time both of these field theory limits. If you imagine the limits where you squash this disk down to look like a flattened line, but you can squash it in either direction, and the same mathematical expression has these two limits, which could be thought of as particle exchanges, or combined together in this way. And string theory was an attempt to explain the fact in mathematical descriptions of the strong interactions why you didn't have to, if you had enough particles exchanged here or here, you didn't sum these two processes. Each one was sufficient. That led to this unified description. And then the same kind of duality was discovered between when one went to quantum strings, quantum corrections to string theory, between ultraviolet behavior and infrared singularities, which is the relation between gauge theories and gravity. So now the place this first occurred, even before one was thinking about strings and these mathematical constructions, before string theory became string theory, you considered, in modern language, two strings coming in, and you see, here we have a diagram, which is now a two-dimensional world sheet of the string, which is a disk with an annulus, and these two other strings are going out inside like this. Now, what does this describe? These are strings coming in. This looks like a loop, right? It can be regarded as a loop of open strings going around. So this is a correction to two strings come in, there's a loop, two strings go out. But instead of thinking of an open string with ends going around the loop, you can think of it as a closed string going out this way, right? There's no loop, so it's a tree diagram. And you can see that geometrically if you take this diagram, take the inner circle, pull it out. Remember, this is a surface here. Pull it out, you get a cylinder, right? This is the bottom of the cylinder. This is the top of the cylinder. And now you see the closed string going around the cylinder. Right? No, the open string going around the cylinder and the closed string propagating. Here, this is the open string going around the cylinder, halfway, one loop, or a closed string going this way. So this is a dual description of open strings the quantum loop correction to open strings being equivalent to a propagating closed string. That means that if you have open strings and construct the quantum theory describing open strings, you're going to get closed strings, gravity, automatically. And if you see how that works, turns out that the ultraviolet behavior of the open strings, which governs this loop diagram, which, since it's a vacuum diagram, knows about the density of states of the open strings. How many open strings there are with energy m increases exponentially. It's characteristic of a string theory. So all these vibrations. That gives rise, in this channel, to the infrared singularities, the presence of poles in the propagator of closed string, the existence of gravity. Okay? So again, this duality that relates open strings we use to describe gauge theories, closed strings we use to describe gravity. Now this took a whole new point of view when D-branes were discovered in the 90s. And it was realized that open strings really should be thought of as ending on extended objects in string theory called branes. Could be thought of as solitons of a closed string theory. And open strings end on them. Their endpoint can move around on the D-brane, which is, it can be a submanifold of the full space. These D-branes are dynamical. They curve, they fluctuate, they can have any dimension. And they source a gravitational field. So, before I started with open strings, quantum amplitudes, you see closed strings. Instead, you can start with closed strings, which describe just gravity, and then find open strings as objects that describe the dynamics of these D-brane solitons, if you want. And if you put these D-branes in, they'll affect the geometry. And that led to discussing what happens you put in a lot of D-branes whose low energy modes are strings. You discover that the quantum numbers, the SU3 of QCD, say, would be simply 3 branes, are the labels of the brane. And finally, the famous and useful correspondence between particular quantum gauge theories, which describe the dynamics of these branes, and quantum theories of gravity, in which these branes in a larger dimensional space are the source of curvature and the geometry. So this is a fast and probably for most confusing description of this, where we are sort of today, where we have this very powerful dual picture between gauge theories and open strings and closed strings and geometry. And in a sense, it can be thought of, there are so many things we've learned from this duality, which is indeed almost 40 years old, going back to my original description, as a geometrization of the renormalization group. And we're in the process of geometricizing other facts about quantum field theory. But the renormalization group, which I discussed, is one of them. And you might have motivated it, that's not how it came about, but in the following way. Imagine scale transformations. You want to go to larger scales, as we said. Well, let's add a new dimension, one new dimension, u, to our discussion. and scale it the opposite way. And there's a nice higher dimensional, or say 5-dimensional, we start out in the real world, geometry, which is invariant under such scale transformations, which is where you take the ordinary metric of space, 4-dimensional space-time, you multiply it by u squared. So so this cancels this when you rescale x's. And then you add du squared, but you have to divide it by u squared to make it scale invariant. And this 5-dimensional space-time is actually scale invariant. It's actually conformally invariant under the conformal group. So all I've done is try to interpret scale transformations, which you do when you discuss the renormalization group in terms of the boundary, fixed u, if you want, projections of a bigger space in 5 dimensions, which is conformally invariant. Now, this is an interesting space. This is known as ADS, anti-de Sitter space. It's the solution of Einstein's equations with negative dark energy, negative cosmological constant. There's negative curvature, and the so-called ADS-CFT correspondence is going to be between conformal field theories, scale invariant theories defined in this space, and theories of gravity, more precisely quantum gravity, more precisely string theory, in ADS space with one extra dimension. And, oops, what was, so that is, I mean, everything I've done is just kinematical. It doesn't tell you that there are such theories, but it turns out to be the case. And this is just Escher's beautiful description of hyperbolic space, of anti-de Sitter space, 2 dimensions. Anyway, so the remarkable thing that these investigations led to in the end was a realization that you can find such a strict duality between theories defined in this extra dimensional space, ADS5, say, and the boundary of that space, the conformal boundary of that space, which is Minkowski space. Now, ADS5 as a geometry, so it's a negative curvature, it's not like a sphere, it's the opposite, is like putting the theory in a box. Very difficult in gravity to put the theory in the box because the box has energy and it's going to pull on itself and collapse. But this provides a box. In what sense is it a box? Well, if you go out spatially, fixed time, go in a spatial direction, say with a metric I showed you, it's infinitely far away. So there's no real box there in that sense. But if you shine your laser in some direction, light rays will bounce off the boundary and come back in a finite time. So there is a boundary there. And at infinity, if you want, spatial infinity, if you put a source, you better specify boundary conditions, because what happens is the boundary can affect you in a finite amount of time. And that the boundary is equivalent conformally to Minkowski space, and that's where you can put a source. And you can have dynamics on the boundary, specify the boundary conditions. You can put in a source. And in this theory of strings, or quantum gravity, or Einstein's theory in ADS5, there are fields, and they're related to sources that you put in. Operators, remember, have dimensions, and the dimensions of the operators are related to the masses of the fields in the boundary. And there is a precise dictionary between observables, between physical observables, all physical observables of the boundary theory, which happens to be the simplest example, a kissing cousin of QCD, highly supersymmetric version of QCD, but very similar otherwise. And here, string theory. And so the correlation functions, the partition function of the conformal field theory, in particular supersymmetric QCD, can be related to the theory of quantum gravity with the insertion of operators at the boundary, or which are well-defined physical observables in a theory of quantum gravity. Now, this development has had enormous impact on the way we think about string theory, and the way we think about quantum field theory, and the way we even think about condensed matter physics. Because it geometricizes many of our concepts. The renormalization group, for example, is simply motion into the bulk. But many other things, more recently, having to do with the structure of quantum states, like entanglement. It's also provided a very useful tool. You can, calculations that are easy in the bulk gravitational theory, solving Einstein's equations, which is very easy compared to solving quantum field theory, can be used to calculate things like transport coefficients and quark law in plasma, and at quantum critical points of theories that correspond to strongly coupled many-body systems, relating them to properties of black holes in ADS5. As an example. So enormous insights into the gauge theories, the string theory description of confining theories like QCD, transport coefficients, maybe construction, exploration of universal properties of quantum phase transitions. But, for many of us, the most interesting things is try to use the gauge theory to learn about quantum gravity. And that's sort of, I would say, beginning, and most provocatively new concepts of space-time. So let me come back now to what is the framework of theoretical physics? Well, as I said at the very beginning, the framework of theoretical physics is quantum field theory. But what is quantum field theory? Well, I gave you two answers, the 1950 answer and then the 1980 answer, and now we're in 2014. So quantum field theory, first of all, is not a theory. And I like to distinguish. Quantum field theory is a framework. Quantum field theory doesn't predict very much. It predicts that they're antiparticles. It predicts spin statistics and CPT. But beyond that, you need a real theory like the Standard Model to make predictions and to test it. Quantum field theory, like quantum mechanics itself, is a framework. There are an infinite number of quantum field theories. You have to put in some other information to get a theory. And what I mean by a theory is something you can make predictions, it can be falsified. Very hard to falsify quantum field theory. As I said, there are only a few things that it predicts independent of the specific theory. We're not even sure about that. Actually, this is a slide I didn't finish because it's so hard. I tried to picture the space of quantum field theories. Wilsonian approach to quantum field theories, one talks about the space of quantum field theories and the flow, from a UV fixed point as you go to the infrared to perhaps an infrared fixed point, or starting with the conformal field theory in the ultraviolet flow. I didn't manage to finish the slide. I couldn't even capture the vast infinite space in which we can even, which I think is still a teeny part of the space of quantum field theories. And it's totally ill-defined. There is nobody knows how to define the space of quantum field theories. Now, for the purposes of discussing critical phenomena, it's not so bad because of this convergence to a submanifold. All those infinite number of irrelevant terms are irrelevant. But if you want to go in the opposite direction, towards arbitrarily short distances, there are indeed an infinite number and no control over that space at all. Not only that, there is string theory. Now, string theory originally thought was a new kind of theory, different, radically different. And, but it isn't. It's the same thing. Because we have all these examples where it's identical to a particular quantum field theory, and all quantum field theories, or most, can be related, and string theories can be related by continuous or discrete transformations. So the way I look at it now, we have this framework, and we have a large extension of this framework. In this framework, space-time is a rigid Einsteinian thing that sits there classically. In this framework, it's dynamical. Sorry, Einstein always told us it was dynamical, but here it's even quantum mechanical and dynamical. And they're extended objects, which can be used to calculate, to systematically construct quantum states in this extended framework. Here we just use particles to perturbatively construct quantum states, but neither of those are adequate to describe the true non-perturbative nature of either of these frameworks. This one is better defined as long as gravity is not, space-time is not dynamical. We can put the theory, the solutions of the theory often on the lattice, solve it numerically. This one, we don't even have the equations or the Hamiltonian or Lagrangian. We just have techniques, tricks for constructing perturbative expansions using strings and set of particles or sometimes branes. So what is the framework of theoretical physics? The true answer is we have no idea. We have no idea how to even formulate it, what the boundaries are, or what the rules are, the equations, the thing that replaces the path integral with the action, or anything like that. So we're in a period, truly, I believe, of confusion. And we certainly don't have anything that picks out the standard theory or its generals, or its what comes beyond it. So we have this incredible framework, not theory, that includes strings, branes, particles, all tools for perturbatively, semi-classically constructing quantum states that are consistent. Probably in this framework, all consistent quantum field theories and quantum gravity reside, but who knows what else. And what is certainly missing is exactly a theory. A principle that picks out a solution. And unfortunately, that means, in the interesting cases, not a static solution, a bunch of particles and their interactions, but a cosmology. Because in this framework, and what we're looking for is a solution to the framework that includes dynamical space-time. So the solution is that of dynamical space-time. What fixes the dynamics, or what fixes the initial state of a time-dependent solution, who knows? And space-time itself is beginning to seem like a derived concept, something that isn't, as a priori necessary for even the formulation of certainly the framework or the theory, because in the framework, all of sort of the sacred features of what we think of as space-time are challenged. In the string theory extensions of this framework, manifolds need not be smooth. You can change the topology. And as we just saw in this duality, the number of dimensions isn't even fixed. We can describe the same phenomena using theories in different numbers of space-time dimensions. So we suspect that space-time is emergent. Now, if space-time is truly emergent from something else, that might be the answer, the way we're finally going to get a description of this framework in its totality, and of course, dynamical space-time is gravity. Now, even though we have all these dualities, we haven't really done away with space-time except in one corner of this big framework called M-theory, which can be described in a limited region with limited power in terms of a quantum mechanical system with no space at all. Just spins, or matrices more precisely, interacting. They appear in the Hamiltonian, you have looks like there's no space. There's time. But that seems to be dual, we believe, to a theory which in one of its limits is gravity in 11 dimensions, supergravity in 11 dimensions. So all of space emerges. But in some sense, all of space-time, but in a very special case where time is very, very simple. And nobody has any idea of what it would mean to have a emergent time. And that might be necessary for really understanding the extent of this, whatever framework is going to replace quantum field theory / string theory. So, to conclude, over time, I'm sure, quantum field theory / string theory is alive and well, which means it's in a period of utter confusion, growing and changing rapidly. Thanks. Massimo.
Of course, to arrive at the synthesis of this kind of model, etc., we had very important data from experiments that the half-50 events that were fundamentally going towards a pattern model. Here it seems that we are tackling a much more complicated problem, and the experiment is not there to help us. So it may take a little longer than, say, 40 years.
That's not a question, but a comment. And I agree, but there's no choice. Besides which, so I tend to be always optimistic. It could be just a few brilliant ideas. It could certainly be a few amazing discoveries that would help us. I mean, experimentalists can make theorists' tasks much easier, of course. But, until we get some of those, we do what we can. There's no sign to me that this expansion of quantum field theory, this growth in what we understand as the framework, and the phenomena that it can describe, especially gravity, has been, can't imagine it being much faster. It's been taken a long time, but it's very lot of work and deepening of the understanding has taken place. So, it's not up to us how far and how long this is going to take, but I see no reason to despair.
More questions?
Are there any implications for any experiments that you get as a result out of this, which will be crucial to the theory?
Well, experiments can mostly give us hints about what we can't think of, but the way we don't have a theory. We have a set of methods for constructing quantum states. And you can pick one of them. Standard model is one of those. And having picked it, guided in that case by experiment, We can then test it over and over and over again, which you've been doing. To go beyond that, gravity and unification, which there's these strong clues, come together. The natural scale, remember this decoupling of scales? Well, it's very nice to do QCD, standard model, at 100 billion electron volts and not to worry about what's happening at 10 to the 19 billion electron volts. But if you turn that around, it means that it's very hard to get clues from experiments since the mass scale is so high. And gravity is such a weak force that you have to go to those distances or those short distances, those high energy, to see its effects. So we have wonderful theoretical problems having to do, say, with the behavior of quantum gravity in the vicinity of black holes. But, that's pretty hard to test experimentally. So everything gets harder and harder to test experimentally, and we desperately look for clues, and there are places we might find them, even at these very high energy scales. In the cosmic microwave background, for example, people hope to find clues to the early history of the universe. And there are other places where it might show up. But if we can't get direct clues, we have to rely on as many indirect clues as we can, and to go on. So at the moment, there are no direct tests of the basic ideas of string theory. What you can do, and some colleagues do, is within this extended framework, construct a particular quantum state, often called a solution of string theory, but they're not really solutions since there's no equations. But they are consistent quantum states that you can construct in a controllable fashion, which might describe the real world. That's analogous to looking for a specific quantum field theory that's part of the quantum field framework that you could compare with the real world. And people are doing that. But we need, it's not enough to post-dict what's already been measured. You want to make predictions, as you say, so you can test theories. That's tough.
You implied that we were lucky that nature had these four hierarchies of space and time, and that you're now down to the fourth level. And you
Four.
implied
What are the four? Oh, you mean in scales?
Energy and space.
Yeah. Sure.
Are you confident that that's the end of the line?
No, not at all. No. I'll address that tomorrow. No.
No. But I thought you said that you were looking for a perfect theory. How could
Right.
it be a perfect theory if it's not the end of the line?
I'll address that tomorrow.
How do you feel about anthropic arguments in physics?
Does that answer your question? Oi. I already answered that question once today. Ask one of the students who. What?
We want to hear.
Oy vey.
Maybe a related question is, what about dark energy and all these?
Well, so I showed you how QCD qualitatively, within a factor of 10 or so, explains 10 to the minus 19. Right? The proton over the Planck mass, right? This is not really a puzzle. And if we believe in unification at the Planck scale, this is sort of predicted, this order of magnitude. So, if you want, really, in a sense, that's my hope. The cosmological constant problem is if you take the fourth root of the energy density to get a mass, is a similar kind of number. And I expect that someday we'll figure out how to calculate it. Much as Dirac, when he pointed out these very small numbers, I doubt if he could imagine understanding why the proton is so much light than the Planck mass, which is one of his big numbers in effect, using the physics he knew at the time. So I don't like attempts to say that is something we can't calculate because we don't know how to calculate. I regard that as a cop-out. But I don't know how to calculate it either. But so what? There are many things in physics that we didn't know how to calculate at some stage in our understanding. What's unusual about that?
So you're saying it might be what you call the technical problem?
No, this is not a technical solution. This is a deep solution. It requires understanding, this asymptotic freedom, this phenomenon.
No, but you wouldn't have to
I can imagine.
change the theory.
Well, I think the cosmology, since we don't have an explanation of how you could get an energy scale that is so much lower than all energy scales we know by numbers like this, I suspect that something new will be required. The other analogy I like to give with the cosmological constant is, so I do believe we don't have a theory. We don't even know what the total framework is. And there are many places where some of our concepts, the most fundamental concepts, are being challenged. So I believe that as we challenge those fundamental concepts, they might very well be replaced by something else, some other enlargement or change even of the framework that we're exploring. And that having done that, we'll be able to answer that particular large number problem. And what bothers me is that some people say, okay, we have this insoluble problem, so we have to give an anthropic argument, which at any point in the 400-year-long history of physics one could have done, and some people did many times. And what's the point? We only started thinking about this problem for 20 years or so. Actually, it's not true. People did think about it before. But it is a kind of problem that has something to do with the global geometry of space-time. We're in a situation we have no idea what fixes the global geometry of space-time. And it's one of the things you better understand if you're going to solve. If you want to get to the stage in describing a theory in which you deal with quantum gravity with as much perfection as we've dealt, say, with a nuclear force, right? You would have to have a theory which explains the Big Bang. Now, I can't imagine doing that either, but that's required not just to answer this theoretical issue of why can't you calculate a dimensionless number that is very small. That's a theoretical problem. It's not an experimental problem. It's not a crisis that requires new space telescopes that will measure this number, the number in front of 10 to the minus 120 to 10% accuracy instead of 30% accuracy. Who cares? It's a theoretical problem. It's a problem because you can't calculate it. And it seems so small and so crazily small that it's a problem. But so is this a problem. And there are many other small numbers. The hierarchy of the weak scale compared to the unification scale has been driving search for the Higgs and supersymmetry for decades. We all believe we're not going to have to, well, some people even argue that that's entropically. I regard that as a cop-out. I can't give you the answer.
Okay,
Yeah.
Just coming back to this, there was this very nice argument in theory because of the test matrix formulation, you cannot really have a really constant cosmological constant, positive one. But
You can't have a what?
you cannot have a de Sitter space, so the true de Sitter space. not do it. Why nobody is using that argument? I mean,
Well, you know, it's very hard to argue that you can't have something when you don't have, you know, you don't know what the boundaries of the framework are. Remember, you know, at the beginning there were 2 string theories, then there were 5, or there were 3 string theories, then there were 5 string theories, and then there were thousands of string theories, and then none of them are theories. And, you know, string theory, or this general framework, is not one that starts with principles. It just invents new ways of doing things. So people have been trying to find, in fact, many people have claimed to have found string theory solutions in de Sitter space that describe de Sitter metastable states, if you want. Now, they're not, in my opinion, solutions or even consistent quantum states over the full space-time history. But, you know, when people talk about the string landscape, they don't talk about the infinite number of well-defined string states that can be constructed, like flat space, supersymmetric. They're talking about the presumably finite number of metastable string state solutions that live in de Sitter space. So maybe you agree with me, those aren't really very healthy.
no.
Okay, so we both agree, but most people don't. Most string theorists will talk about those as the landscape.
No, but my point was, why not use this as for the advantage? Because
Well, but I refuse to use it as an advantage because I don't know what the principles are that say that there are no such. There might very well be principles. De Sitter space is very strange. So is the Big Bang. De Sitter space is strange in the end as well. You know, the universe splits up into these arbitrarily small, causally connected regions. It's totally nuts.
So you don't buy this S matrix argument? You think that they are not correct? The fact that S matrix formulation requires that you have possibility of flat space.
Well, you know, if you, as I said, that's the future problem. So I'm suspicious that we need to understand in any theory of dynamical space-time both the beginning, which is common to all geometry, all cosmology so far, and the end. Physics is time symmetric. So you're describing a problem of the end. How can you do measurements in such a space-time where these asymptotic states will each be in a separate, causally disconnected portion of the universe? So that's true. Does that mean you can't consider such mathematical solution? Obviously not. But I think we're not at a stage where we can come to such strong conclusions, therefore.
If there is any urgent question, okay, otherwise, let me propose to thank David for